Today we're going to do an activity, the purpose of which is to see if the law of conservation of momentum, that law that I told you about on Friday, Monday, and Tuesday, the law that says momentum can't be created, it can't be destroyed, the momentum always stays the same in an isolated system. We want to see if that law of conservation of momentum is in fact valid. We know that it is, right? We know that it is. Well, we're going to verify that it is. We always phrase our problem in the form of a question, so we're going to phrase it like this. Is the law of conservation of momentum for the collision of two dynamics carts, in this particular situation, okay, in this particular, these particular dynamics carts? Here's how we're going to do this activity. We'll talk about the iPhone interface and stuff a little bit later. Okay, right now let's just focus on the main point of the activity. Hey, we're going to have 10 trials going here. Okay, 10 trials for each group. And in each trial, you're going to send one cart down towards a second stationary cart. You're going to push the first cart down towards the second stationary cart. They'll collide. They'll stick together. They're going to stick together because you're going to put sticky tack on both of those, which is going to allow them to stick together. And then they're going to move off as one object after the collision takes place. Hearing what I've just said, which is not every detail that you have to know, we'll talk about more details in a few minutes, but hearing what I've just said, can you tell me what the manipulated variable is? The variable that you are going to change. Very, very close. Okay, the speed of the first car is what we heard here first. The speed of the first car. Is that right? Almost. Okay, in the end, we're going to use changing the speed of the first car to change something else in the first car. What we're trying to test here is the law of conservation of momentum valid. What do we want to see about? Not the speed, the initial momentum, right? So it doesn't matter how we change that momentum, we're going to do it by changing the speed. You could also do it by changing the mass. Doesn't really matter. We are changing, consciously changing the initial momentum of car number one. That make sense? What's the responding variable going to be if we're changing the initial momentum of car number one? The final momentum. That's going to be the final momentum of car 1 and 2 combined. And then, of course, your control variables. I'm not going to give you these ones. You should come up with 3 or 4 good control variables, 3 or 4 variables that need to stay the same. Don't mention things like temperature. Well, ideally, the temperature should actually stay the same, right? Everything should stay the same. Okay, but that's not a real important one. Okay, I want you to identify 3 or 4 good ones, 3 or 4 things really important to keep the same through this experiment, okay? This is what your apparatus is going to look like. You can see in the top left-hand corner, there's a triple beam balance scale. The first thing you're going to do here is measure the mass of each cart. Cart number 1, that's the cart that you're sending down towards the stationary cart, cart number 2. Cart number 1 will, in all likelihood, be one of those silver carts that you see on the screen now. Okay, cart number 2 will be this black cart. Okay, cart number 1 slides nicely along a dynamics track that you see there. We don't actually have enough tracks for everybody. That's okay. It works well just on the floor as well. Okay, but if you have a track, you will find that the first cart, the one that you're sending down towards the second one, again, fits nicely along the grooves of that dynamics track. Okay, so cart number 1, moving forward, cart number 2 is initially going to be at rest. Both of them are going to have a little bit of blue sticky tack on the sides of them here. And the reason you're going to do that is to allow them to stick together when they hit each other. Now this little thing that you see right here is called a motion sensor. That motion sensor will be plugged into a little thing that you see right here called a AirLink. Okay, it's an AirLink 2 actually, AirLink 2 apparatus. It's going to look a little bit different than this. That's okay, don't panic about that. When you turn this on, and I'll tell you how to turn it on in a few minutes, it's a little bit different than you might think. And when you turn it on, then the data for position and time of whatever it's detecting is going to be transmitted from the motion sensor all the way through here to this AirLink apparatus. Then it will be beamed wirelessly from the AirLink apparatus to your iPhone. You're going to see a real-time graph of this data being plotted on your phone. So as this cart number 1 goes down towards cart number 2, you're going to see a graph being plotted instantly on your iPhone. as cart number 2 gets hit by cart number 1 and they go off as one object, you should see the graph changing because the speed should change, right? Speed should slow down as both carts combine and go off as one after. And you're going to see that graph instantly on your iPhone. Now, once you have that graph, to be honest, the graph isn't so much what we want on the phone itself, it's the data that we want on the phone. You're going to email that data to yourself and to your partners. And then you're going to go back and use Microsoft Excel to analyze that data. And I'll show you how to do that in a little while as well. Make sense? That's trial number 1. Then you're going to do it again. But you're going to do it again manipulating the momentum of the first cart. So you're going to send it down with a slightly different speed. So it has a different momentum. Okay, get trial number 2. Get data. Email it. You can email, I think it's up to 4 of them at once. So if you want to do trials 1 through 4, then email it. Trials 5 through 8, then email it. Or you can even wait till you're done all 10 trials. Email the first 4, then email the second 4, then email the last 2. That's fine too. It doesn't really matter. Just get all the data emailed to yourself and to your partners. By the way, this is a magnified version of this, of the motion sensor. There's a little switch on top of the motion sensor. It's not an on switch. There is no on switch on this. Okay, it's a switch that directs it either toward a little picture of a person or of a little cart. You want it on the little cart. If you put it on the person, what it's going to try to do is measure the position and time of something big and something far away. If you put it on the little cart, that's where it is right now, and that's where it will likely be on the apparatus that you get, probably be there already. Then it's going to measure the position of something close and something small. In other words, a dynamics cart that you're using in this experiment. You should see a graph that looks something like this plotted instantly on your iPhone. Okay? I don't care what this looks like down here. You might see kind of squiggles everywhere. That doesn't matter. You won't see it going back in time, that's for sure. But you might see it squiggling like this. That's okay. I don't care about that because when you email that data to yourself and you go to analyze it, you're going to delete that data anyways. Tell me what's happening in that set of data right there. Kind of. Natasha? Yeah, the cart's not moving at all. This is collecting data before I push the cart. That make sense? The position is effectively 0 there before I push the cart. So you're going to ignore that data. I'll show you how to do that on Excel once we get through this. What you should see are 2 distinctly straight lines. You might see some stuff up here as well. Doesn't matter. Okay, that's after it stopped or when it was slowing down or whatever. Doesn't matter. Okay, we want 2 distinct straight lines in between. That first straight line will correspond to what? It's a position time graph. The slope of a position time graph is what, Tristan? No, not the acceleration. It's the initial velocity. So this will be VI. This will be VF. You would expect to see it slower, right, and therefore a smaller slope, because when 2 things combine, more mass, it's got to be going slower, right? This is your first graph. You're going to do this on Excel because Excel will allow you to get the slope of this graph, the slope of this. Okay, it'll allow you to get the slope of both of them and therefore get VI and VF without going through the process of calculating the slope by hand. Again, I'll show you how to use Excel once we've collected our data here. This is trial 1. You're going to have the same thing for trial 2 and for trial 3 and so on. You will have 10 graphs that look like this. You will have 10 different VIs. You will have 10 different VFs. You're going to record all that stuff on a table that looks like this. M1 and M2, that's the first thing you recorded, right? Then you're going to have VI and VF for 10 different trials coming from those graphs. Once you have VI and VF for 10 different trials, what do you think we're going to do? What comes next? Nope. We're never going to average data points on a data table. Whenever you see a data table, 99.999% of the time, you're going to do this. Nope. Not going to calculate anything from it. When you see a data table, you're going to plot a graph. Okay, that's what you're going to do every time. The graph is going to be VF as a function of VI, or VF versus VI. And it will work out to be a straight line, or it should work out to be pretty darn close to a straight line. Now, here's the new part of it for you. Here's the part that you've never done before in physics. Okay, it's a little bit of a mathematical analysis that we're going to use probably about a half a dozen times this year. It's really important. We're going to first write down the equation for this graph. We know the equation for this graph already, if we think about it. Go back to grade 9 math. The equation for any straight line graph is what? Rise over run is the slope. The equation for the graph itself is? Good. So the equation from the graph is y is equal to mx plus b. Again, you're going to have to do this analysis probably a half a dozen times this year for different graphs. It will always start out this way, with y equals mx plus b. Now what we want to do is tailor this equation to this specific graph. Not the general form of it, but the specific form of it. The y-axis here is VF. What does m stand for? The slope. I'm going to write the word slope in. Anybody have any idea why I want to get rid of that term m for slope? Yeah, exactly. We don't want to mix it up with mass down the road. So let's write the word slope in. The x-axis is going to be v1i, the initial velocity of car number 1. B stands for what? B is the y-intercept. There will be no y-intercept here. And the reason there'll be no y-intercept is because, think about this, if v1i is 0, okay, if v1i is 0, car number 1 isn't moving, then how fast are the two of them moving after the collision? Well, there is no collision, so they're not moving at all. So you're going to have a point that's 0, 0. It should go through the origin. There is no y-intercept. Okay, so far so good? There's the equation for my graph. That's easy enough, I think. Now we got to get an equation from our data sheet or from some kind of concept that we know. A data sheet or a concept. Well, the concept that applies here would be conservation of momentum. Pi is equal to Pf. The initial momentum would be m1 v1i plus 0. Why plus 0? m1 v1i plus 0. Why? Right, second object is at rest, therefore it has no momentum. Equals, well, they're sticking together after the collision, so we're going to say it's mvf. Good? Let's get rid of the 0 here just to tidy it up a little bit. I just wrote that in there so you could see what was going on. Now I want to rearrange the equation either from my data sheet or from the concept, this time, in this case, the conservation of momentum concept. Rearrange it to solve for the same variable we have right here. Okay, we've solved for VF in my equation for my graph. I want to solve for VF in this equation as well. VF becomes m1 over m times v1i. Make sense? I've solved for VF in both cases. Now comes not necessarily the hardest part of it, but the most important part of it. Cross off things that appear in both. VF appears in both. V1i appears in both. What am I left with? The slope is equal to m1 over m. You guys know that the slope of a position time graph is velocity. You guys know that the slope of a velocity time graph is acceleration. How do you know that? How do you know those two things? Yeah, okay. Some of you may have figured that out. Most of you know that the slope of a velocity time graph is acceleration because your teacher told you that in Physics 20. Okay, that's why most of you know that that's the slope of a velocity time graph. Today we're learning how to find what the slope of a graph means, even on a graph that we've never seen before, so that the teacher doesn't have to tell us. Okay, does that make sense? The slope of this graph isn't quite as easy as the slope of a velocity time graph. The slope of this graph is m1 over m. And what does m stand for again? Mass, yes. But which mass is it? It's both of them combined. It's m1 and m2 combined. Make sense? Now, You're going to get the slope from Excel. You're not going to need to calculate that by hand. The Microsoft Excel, the graph that you plot right here on Excel, will give you the slope. You're going to calculate this. You're going to calculate this. If these two numbers are the same, what have we just found? The law proves to be correct. Well, how do we make that conclusion? We made an assumption here. We assumed that this is valid, correct? We assumed that this is valid. If the assumption that we made leads to this number being equal to this number, which it should be, then the assumption that we made must have been a correct assumption. If they don't equal each other, then the assumption that we made, PI equals PF, must not have been a correct assumption. That make sense? So let's get this number. Let's get this number. Let's calculate a percent difference. And if that percent difference is less than about 10%, let's say it works. If it's greater than 10%, let's say, yeah, law of conservation momentum is proven wrong. Make sense? Of course, once you have this, either proven or disproven, you got to conclude something. Your conclusion is going to take two parts. One, you're going to answer the question, was the law of conservation momentum verified? Yes or no? It was verified. It wasn't verified. How do you know? Explain how you know that it was either verified or wasn't verified. And that comes back to this, right? How do you know? Well, if the slope equals m1 over m, then yeah, it was verified. If the slope is not equal to m1 over m and it's greater than a 10% error, then it wasn't verified. Okay, that's your explanation. And then finally, you're going to need some sources of error. 2 or 3 good sources of error. It may have to do with the apparatus. It may have to do with the procedure. It may have to do with your time management. It may have to do with anything. Don't say something like, I hate this one when I see this, calculation errors. You make calculation errors, then fix them. Okay, that's not a source of error. Give me your possible improvements for those sources of error as well. Okay, there's a few pretty good ones for this. Okay, if you stop and think about those sources of error as you're working, okay, as you're doing something, you're thinking, oh man, like, too bad we didn't have this, okay, or too bad we didn't do this, or whatever. Write those down. Okay, make notes so that when you go to write this up, it's all good. Is that relatively clear? Okay, I'm going to hand out in just a second here a piece of paper to each of the people that are using the app on their phone for this. Okay, that piece of paper will have instructions as to how to connect it via Bluetooth. It will also have instructions as to how to collect the data. Follow it to the letter. Once you've got that data in your phone, again, email it to yourself, and you can at the same time, if you want, email it to your partners as well. Okay, worst case scenario, email it to yourself, and then you can forward it to your partners if you want, okay? And then finally, write the lab up. There's going to be quite a bit of work in writing this one up because you've got 10 graphs that you've got to interpret 2 slopes from each of those graphs to get VI and VF for 10 different trials, and then turn around and plot a new graph of VF versus VI. So you're going to have a total of 11 graphs and 21 slopes to find here. It's going to be quite a bit of work. Once you're done all that work, what are you going to do? Submit it to me. How are you going to submit it to me? Through Google Drive, like we practiced here, what was it, a week and a half ago? Good news is, the due date for this was originally Monday. And then I realized this morning, as I was telling my class that, hey, we don't have school on Monday. So we're going to make the due date a ridiculously long week and a half, the Monday following the break. It needs to be... Not sure where I just left off there. When I paused it, that's okay. Assignment is due on Monday, week and a half. Okay, submit it via Google Drive. And if you have any questions, just let me know. All right.